say that it represents what? Represents mass, no, represents relative abundance, or we call it intensity in some of the references, intensity versus what? Versus mass to charge ratio value. I mean that in x-axis. Okay? That's what I've taught you. Or this the summary of what you've been learning. So we say that we can use, we as chemists, we can use the basic operations of what? Of relative abundance or intensity, okay, relative abundance of or intensity, and mass to charge ratio of all isotopes present in the element, for all isotopes present in the element, to calculate the relative atomic mass. To calculate the relative atomic mass. So the question that now you have in your mind, how? So you have two cases. So case one, we say that if the plot or the mass spectrum is representing intensities versus atomic masses. Case one, we say that if the plot of mass spectrum represents what? Represents intensity in y-axis, intensity, let me just write it help in y-axis, versus what? Versus mass to charge ratio. Mass to charge ratio, which is this one. So let me give you a sketch. So what do you mean? In y-axis we have intensity, and suppose that we have introduced a sample that have 3 isotopes, right? So 3 isotopes. So please watch carefully on this diagram. I think that's better if I draw it. Let me draw it there, or draw in the next column, so you can see everything that I want to teach you. Do you enjoy advanced chemistry? Please tell me in the comment sections if you are enjoying this session. And please tell me where are you from. You are watching, or you are watching this video where in Africa, where in Europe, where in North America, in South America, in Asia, in Australia, if it is in Tanzania, in which regions, in which district, in which ward. So tell me please in the comment section. So I mean that let me represent the graph for the first case. I've prepared the questions on this concept or on the first case. We have the intensities, and then as I say that, suppose the element has 3 isotopes. So how many peaks will you have? 3 peaks. So this one, suppose that the mass to charge ratio 1, mass to charge ratio 2, mass to charge ratio 3. So again, for this case, we have what? Intensity 3. And then for this case, we have again what? Intensity 1, because it's the first peak. And then for this case, or at this point, we have what? Intensity 2. So these are the intensities versus mass to charge ratio of each isotopes. So remember that this line, full line, and this one, this we call them in chemistry isotopes of what? Of a certain element. Let's say element X. And in this axis we have mass to charge ratio. So now, so that the first case, for example, that if you want to derive, because we follow some steps. So this is the first step on this derivation. So here we have a little subtitle which is called derivation of the formula, derivations of the formula of finding relative atomic mass. So that the first step, we say that consider plot 1.4 below, and this is figure 1.5, which you call the mass spectrum. So we say that the second step now, okay, the second step, we say that the mass, the relative atomic mass, the relative atomic mass for this case is given as summation of what? Summation of the product, for that case, product of intensity and the isotopic masses. Isotopic masses. Then this one divided by summation of intensities. Possibly you are from O level, remember that. So second step, we say that general formula. So in this general formula, this in mathematics you call it sigma notation, which means summation. Sigma notation, which means what? Summation. Sorry, it is symbol for summation. So then, for example, relative atomic mass in the plot 1.5, it will be what? The sum of the product between intensity of the stream of the isotope and this what? Mass to charge ratio divided by the sum of these intensities. So you see, the sum of this intensity, intensity 1 plus intensity 2, intensity 3, forming denominator of this formula. And then the product between I3 and the M3 plus I1 and the M1 plus I2 times M2 is giving us what? The numerator of the formula. So if you want to consider this figure right now, we say that there we have intensity 1, we multiply by isotopic mass 1, plus we have again intensity 2, we multiply by isotopic mass 2, then again we have plus what? Intensity 3, then we multiply by what? By mass 3, and then divided by sum of the intensities, where I say that intensity 1 plus intensity 2 plus intensity 3. So I will teach you and I will solve some problems with you concerning on this concept. So don't do this in exam, but I'm just highlighting this formula because it's very important. So that is in case 1, if the mass spectrum representing intensity vice versa mass spectrum, no, vice versa mass to the charge ratio of an element, and where the number of peaks represent the number of isotopes present in the what? So what if in case that you have two streams, 1, 2, how will this formula be? Take time to think. What if, for example, you have only one, 2, for example, silver has only 2 isotopes. Copper has only 2 isotopes. Okay, so chlorine has only 2 isotopes. So in case of chlorine, we have only 2 streams. Well, how will this formula be? So if you have stream 1 and stream 2, then this part will be omitted. And we remain with this product plus this product divided by this product. So this part will be omitted, and also this part will be omitted. This part, yes, will be omitted. Right? So let us go for case 2. Case 2, we say that if the plot of what? If the plot of mass spectra represents relative intensity, relative abundance, not intensity please, relative abundance versus what? Isotopic mass. Isotopic mass charge ratio. So how are you going to generate the formula for this case? We have this meaning. Suppose also we have an element which having 3 spikes, 3 peaks after it has been introduced in what? In mass spectrum, and that the results. Okay, the spectrum can even spread wider like this, right? So this is mass to charge ratio 1, mass to charge ratio 2, mass to charge ratio 3. Then this is, we say that relative abundance, for example 1, and then here we have another relative abundance. So this is relative abundance 2, but remember that this relative abundance is expressed in percentage. Okay? And then we say that here we have third peak. So here we have semi-relative abundance. So this is the first step. So remember that the part we call it the reversion. The reversion of what? So the reversion of relative atomic mass. So this is the first step. So we go for the second step. The second step that we say the general formula of mass spectrum, general formula of mass spectrum or mass spectrum, general formula of finding relative atomic mass is, we call this one. It's we say relative atomic mass is equal to summation of the product of what? Relative abundance. Relative abundance multiplied by isotopic mass. Isotopic mass, and then divide by summations of relative abundance. Summations of relative abundance. You have to be careful on these two formulas. Summation of relative abundance. Be careful. These questions are very tricky. Relative abundance. So now, if you want to use the symbols that have been used there, we say that relative atomic mass is equal to the product of relative abundance 1 times isotopic mass 1 plus abundance 2 plus isotopic mass 2 plus abundance 3 times mass isotopic 3 divided by relative abundance 1 plus relative abundance 2 plus relative abundance plus relative abundance 3. Okay? In case you have any question, please don't hesitate yourself to ask in the comment section. I believe you're enjoying this lecture. Is it? Yeah, for me I do. Okay, so he said that from that deduction, relative atomic mass is equal to times M1 plus what? Relative abundance 2 times M2 then plus what? A relative abundance 3 times M3 divided by sum of the percent of the relative abundance, which is always 100. The sum of percentage always is equal to 100. So this plus this plus this is equal to 100. So also this is the simplest formula that we might need in solving problems. All right? Okay. So let us see examples now. Let us see examples. In case that you have any question, don't hesitate yourself. Ask in the comment section. Okay, so let us do some examples of using these formulas. Okay, so you have this now is example 1. I've been giving you just a question. A sample of pure unknown element X was analyzed and the data is given below. Calculate the relative atomic mass. Calculate the relative atomic mass of X strictly to 2 decimal places. 2 decimal places. So you'll be given a table like this. This is the symbol of isotope. This is mass, the Chinese ratio in atomic mass unit. This is natural abundance. natural abundance. So here you have symbol of isotopes, and then they'll be given 3 isotopes. So you need 4 rows. The first isotope is Xc1020. Then this mass 19.92 atomic mass unit. Its natural abundance, its percentage, occupied, a lot. Then I have X1021. This is 20.994, 0.257. Then you have this element or isotopes. To 1.991, and then the relative abundance is 8.82. So you have to find the relative abundance when you'll be given a table, and then you can try before, you can pause the video and try to solve the problems. I know you are very good now in general chemistry, especially mass spectrometry. A sample of pure unknown element X was analyzed and the data is given below, here, this table. So not below, in the next column. Calculate the relative atomic mass of X strictly to the 2 decimal places. So find relative atomic mass strictly in 2 decimal places. So this is a symbol for element. Which element is this? If you look at the atomic mass, according to your knowledge of 20 elements in the periodic table. So this is magnesium. So this is the magnesium isotope. Right? No, I'm sorry, not magnesium. This is neon. This is neon, right? So this is neon. Nobody is that they're having this behavior. So we have been given natural abundance, we have been given mass. This is mass to charge ratio in atomic mass unit. That's why the unit is signifying what is it. Right? So let us compute. So for this case, we say that we might go direct, and even something that we might be calling something else. Now the best step, we say that the first step for this case, let us do computation or not, or let us recall the formula of computing relative atomic mass of 40. So we say that relative atomic mass is equal to the product. So what they be given here? Intensity or abundance? Abundance, right? So we say intensity of what? Of natural abundance is the products of what? Of relative abundance and isotonic mass. abundance. In short, isotopic mass. So abundance times sorting isotopic mass, and then divided by 100 because we'll be given abundance. So second state, we have recorded almost everything, but we are still lacking a piece of information. So it's the second step. Compute relative atomic mass by using that form at the step that we are going now. Okay, so how do we compute relative atomic mass? Is the way so relative atomic mass, we say that for this case, it's the product of each natural abundance and it's the isotopic mass. This one times this one times this. Okay. So we say that for this case, how many isotopes we have? 3, right? So it will be abundance 1 plus abundance 2 So that's how we compute the relative abundance. So relative atomic mass next take this mass times this one. Times 90.22, and this one we add again with product of this times this, so it is what? Abundance is 0.257 multiplied by 20.994 plus, again we got the final product 21.991 multiplied by 8.2. Okay, so if you find this product and this product and this product together, you have to use your scientific calculator when you'll be finding the product there. You have to make sure that you'll be accurate and then spend just should be seriously and should be focused on that. We have taken 19.22, but here I forgot the denominator. So the denominator, even if you take this plus this plus this, you get 100. 100. So the 100. So relative atomic mass of element X, this will be equal to 19.2 times this is 19.9.992. I'm sorry. So it is 19.992. 90.22. Okay, so let us do together. You have taken 19.992. 19.992 times 90.22 plus 21.991 times 8.82 divided by 100. So the response for that case, because you have to put your response, okay, in 2 decimal places. So the response in 2 decimal places will be 20.03, not 20.17, 20.03. Therefore, relative atomic mass of element X is 20.03. So that's the response for the first equation. Do you have any question? So if you have any question, please don't hesitate to ask in the comment section. Then I will come back to you. Okay, now let me give you example 2. Remember that these questions appear in final exam and you can solve some. Silver consists of 2 isotopes. 2 two isotopes. Which is silver 47. The isotope of silver this is mass number of silver, it is 107, and the other isotope of silver so you have silver, atomic number is 57, and then atomic mass is 109. Of atomic masses, silver consists of the two isotopes, that ones and that ones, of what? Of atomic masses okay, so atomic masses 106.9. Gram. Atomic masses 106.9 gram a mole. And the 180.9 191. And the 108.91 gram per mole respectively. The relative abundance abundances of these isotopes are 51.88 for silver with atomic mass of 47 and the 107 and the second and 44.0 48.12% for silver, for silver 47 109. So the question asks you calculate the average atomic mass. That the question says that raise the relative atomic mass of silver element. So let us read the question clearly and then we are going to solve it. Silver consists of two isotopes. These are the two isotopes of silver. So you see that the air mass number is the same, 4747. And the atomic mass is not the same. So of atomic mass is 106.9 gram per mole. And then 180.91 gram per mole respectively. The relation or the relative abundances of these isotopes are 51.88% for silver isotope and then 48.12% for silver element. You have to calculate the average atomic mass of what? Of silver. Can you try it? You can pause the video and then try that question, see if you get the right answer. Good, thank you for trying. Let us do correction in case that you missed it. Okay. So again, we say that that's all. That's the main focus that we should have in this topic. So solution, we say that we'll give you atomic masses, gram per mole, gram per mole. We'll be given here the percentage, their percentage intensities. Solution, so you have two silver isotopes as the question has stated, and then he said that the first step we say that data given. This is the data given below there. Then we go for the second step. The second step of solving this problem. You have to recall the new formula. We call the formula of finding relative atomic mass. So that's the first step. So the formula that I have to recall is the one that I've been repeating several times. It's called the relative atomic mass. And this relative atomic mass, we say that is equal to the summation of product of what? Intensity times what? Depends. What are we given past? We'll be given relative boundness. Divided by sum of 40. Oh, sorry. Excuse me, please. I confused with this formula. This should be the product between the relative abundance times intensity. Times isotopic what? Mass. Divided by what? Sum of 40 of relative abundance. Relative abundance. So you say that for that case, relative atomic mass, and then here we say that we have we have the product of relative abundance of the first peak times this mass to the charge ratio. Okay. So here we say that we'll be given the relative atomic mass. We'll be given the relative atomic mass because the question states that silver consists of two isotopes, 1, 2, of atomic masses this. So the relative atomic mass you are given. The relative atomic mass is 106.9. So we said that the relative atomic mass is equal to 106.9. So we introduce it in C position. This is equal to what? Silver consumed the two isotopes of that ones of atomic masses this and that ones respectively. The relative abundances of the isotopes are that at this value is 51.88% for the first isotopes, and then for this one, calculate the average atomic mass of 40 of silver. I'm sorry, we are not given the relative atomic mass. We are given something else. So when you say about data given, you have listed data givens, but you say that we are looking for the relative atomic mass. How many isotopes do you have? 2. So our formula will be mass charge ratio 1 times relative abundance 1 plus mass isotope 2, then relative abundance 2 plus mass, or mass the charge ratio 3 times relative abundance of 3 divided by sum of relative abundance, which is 100. So we say that relative atomic mass, for this case, is equal to what? Mass of the first isotopes. So isotopic mass 160.39. So this is 160.9. We multiply with what? Which it is relative abundance, which is 51.88. 51.88, then we put close bracket because of the space. Then we say plus, again product of what? 108.9. 91 times 40 is abundance. And the abundance is 48.12. And then divided by 100. So relative atomic mass of silver, isotope of silver is, so just use your scientific calculator to do the computation there, and then so 106.9 times 51.8 so plus 108.91 times 48.12 you divide this 100 and the response is 107.89 gram per mole. So this is 107.29 gram per mole. 0.87. Gram per mole. So we just say that according to this sentence, average atomic mass. So we say that the average atomic mass of this element, that is of silver isotope, is 107.87 gram per mole. So I think this is, you see that is how interesting these questions as long as we solve them. So the relative atomic mass for the second example is the one that I've written there. So let us go to the third example. Example 3, concept. There is a certain concept here. Magnesium magnesium have 3 isotopes, stable isotopes. Has 3 stable isotopes. Isotopes of masses 29.985 985 and 4 and 98 5 atomic mass unit. The relative abundances, and I'd like just to leave these questions as your homework. You have to try before we go for the lecture series. The relative abundance so the relative abundances of three isotopes are 30.395, 30.9. Abundances of three isotopes are 39.35, 5.0, 0.65, and 5.585 respectively. Calculate average atomic mass. Calculate average atomic mass of that element. So use the concept that I have taught you to understand that the magnesium has three stable isotopes of masses 29.9 and then 29.985, 24.985 atomic mass unit. So these isotopes has real numbers, but I wrote two. Excuse me, I want to make corrections for this question. It is 23. So let me do minor correction. So that you have accurate data. So masses is 23.98. and 3.985, 24.9, 24.985, and 25, and 98, and 5.9, 82. Atomic mass unit. The rough abundance are 39.355.065 and 5.585. Yeah, everything's correct. Make sure that you try. Make sure that you try to do this homework yourself. Don't ask help from anyone else. And then join me in the lecture series of mass spectrometer. I'd like to thank you for watching this video. Thank you for your time. One thing is, I believe you have enjoyed a lot. Make sure to watch some other videos in this channel called about advanced in chemistry. So, and then make sure to watch some other videos for physics and advanced mathematics and basic applied mathematics. So I think that the sessions was very interesting to you. I thank God who have helped me to teach you this concept. So I would like to ask you that to make sure to try that questions before we come for the third sessions, when we'll be solving problems or some other problems and even conceptual of the atomic structure. So I'd like to thank you once again. See you in the next lecture.